Hey there, in this video we're going to look at the simplest of the numerical integrators. First one we're going to look at is the trapezoidal rule. And just like its name, the way the trapezoidal rule works is to take the integrand and recreate it as a bunch of trapezoids. So we have our integrand f of x with respect to x, and if we integrate between some limits a and b, give it some kind of crazy shape here. And then what we could do is we could take our interval and divide it up into a number of segments, checking for the value of the function just at those certain points. So in this case, this would be a 5-point integration rule where it looks at just the 5 points here. And then it recreates the function effectively as a bunch of straight line segments. And then the integral is the area of these line segments and the trapezoid-like shape underneath them. So if we pick just one of these, say like we pick this one right here, and we look at it a little bit more zoomed in, we have our trapezoid shape, and it has some base width, we'll call that h, where each of these are going to have a width h. In other words, our points are all equally spaced. And we can calculate what h is based on how many points we want to use. So if we have limits a and b, if we take the upper limit minus the lower limit and divide by the total number of points, that'll then tell us how big our step size h is. And then we have these points up here in the corners. Those are going to be the function at point, in this case that would be a, plus we've got an extra h away from a. And then the next point here would be f at a plus 2h. So all along in our trapezoid rule, the points we're visiting are all spaced h apart. So we have a and then a plus h, a plus 2h, and so on all the way down. So for a trapezoid, the area of that trapezoid is equal to the width multiplied by the average of the left-hand side and the right-hand side. And so then the total area under this curve, which is the same thing as the integral, is going to end up being equal to a bunch of these trapezoids side by side by side. Now, however, we do have to be a little bit careful because the sides of these overlap. So like the left-hand side of this first slice is the right-hand side of the second slice. And then the right-hand side of that slice is the left hand of the next. So there's some sharing here between left and right. So let's write down what the total answer is going to be, although you can figure this out pretty quickly on your own. So we're going to have an h for the width divided by 2, and then left hand of the entire interval. We'll have an h on 2 times the function at the right hand of the entire interval. And then we have all those in-between points. And we get to count each of those twice. So 2 times a half cancels out, and we'll just have a single factor of h, and then a summation to represent all those intermediate points, where we'll have some index lowercase n starting at 1, traveling up to capital N minus 2, because we already have 2 if we do the first beginning and end. So n minus 2 are left over. And we have f of a plus an h. Let me just make these a little visually more distinct. And so that's the trapezoidal rule, where we have a total of capital N points. So now we're going to take it a step up. And you can imagine we could do a little bit better than just line segments. We could do something a bit smoother. Trapezoid rule is real pointy. And so the next step up is called Simpsons Rule. And so Simpsons Rule, instead of doing trapezoids, does quadratic curves. So if we take our function something wiggly here and we're trying to integrate it between a and b, so we'll sample a few points along this curve. Now if you're saying, well, why don't I just do the entire curve? Well, numerically, that's actually impossible. That would be an infinite number of values you'd have to visit. So you have to chop this up into some finite amount of intervals to do it in a computer. So anyway, we've got these points here. And the name of the game is to connect these with curves. So a quadratic curve is going to require 3 points. So just like trapezoid rule needed 2 points for a line, you need 3 points for a quadratic. And then you fit these with some kind of smooth quadratic curve. It'll be smooth for those 3, and that would be the first curve. And then you'd have your second curve for the next 3, and so on down your interval. And the basics of what you're going to do here is you would fit the quadratic. So we'll do a coefficient a sub 2 x squared, and then another coefficient a1 x to the first power plus a naught. And you'd be fitting for these coefficients a naught through a2. And we're going to fit this to each set of 3 points. And there's a mathematical way to do that, but it would just take a lot of time and space to write it out. So I'll just summarize that's what you do. And then you can calculate the area. So you could just do a regular analytic integral for a quadratic, and you can analytically get what is the area under that quadratic curve. And so then you'll get the area here in the blue part, and then you'd get the area in the green part, and you just add these together to get the total area. So it's not especially hard to do, but like I said, it is tedious if you're doing it by hand. So that said, we can sort of jump ahead to what is the generic result. And what we're going to get is h on 3 times the function at the far left plus h on 3 times the function on the far right plus 4h on 3 times the summation of f a plus nh, where this would be the odd intermediate steps, plus 2h on 3 summation n1 to n minus 2 for the even intermediate steps. And sorry, let me write that a little bit more clear. Those are n's there, nh. So actually pretty similar in character to the trapezoidal rule. The only difference being that we have an extra term in here for the intermediate steps, and the coefficients are a little bit different. And you might say, well, wait, why don't we just keep going? I've just invented a new rule. We're going to name a new rule after me. Well, you can, but it gets really ugly really fast. And the fact of the matter is this is not really worth it. Like, even if you go many steps here, it's like really high, fitting a really high order polynomial. Turns out you've got a better option, which is something we'll cover in a follow-up video. So let's look at using the trapezoid rule in Python. We can code our own version of the trapezoid rule easily enough, although there is a built-in version that lives in the package scipy. Specifically, it lives in scipy.integrate. Scipy has a number of sub-packages, and the one we want, of course, is named integrate. So we could import scipy.integrate. It's kind of a long name. We could rename it. The syntax I'm going to use here is from. So from scipy, import integrate. So that'll give us the name integrate, and integrate.traps, for example, would give us the trapezoid rule. Okay, so now let's make some data and try integrating it with the trapezoid rule. So I'm going to start with some x values and then y values. My x values I'll just use an a range for this simple example here, but they don't have to be, well, they don't even have to be equally spaced, but they don't have to be spaced with integers. They just have to be some x values, and then some array that we want to integrate. Now let's make our y values let's just do Jenny's phone number. So 8675309. And that, of course, needs to be a list if I'm going to use this syntax. So that's 7 numbers, and that'll be the y values. And we want to calculate the integration of Jenny's phone number. So to do that, I run integrate.traps. And then in here, we want to give the y values in the x values. I just popped up the help here. So integrate y with respect to x. If you leave off x it's going to assume that they're equally spaced 0, 1, 2, 3, 4, 5, 6, 7, which actually happens to be the x values I've created here. But your x values don't have to be equally spaced and don't have to be integer spaced. So you'd want to include them in most cases. So we're going to do integration of y with respect to x and let it print out the results. The integral of Jenny's phone number is 29.5, right? So now you know. It can help to plot what we're doing here. So I've already imported a matplotlib just like I've already imported NumPy. So we're going to do a plot of x and y, and let's make those, let's make it a black line, and let's also make dots and a solid line. So we'll just plot all of those things and see what that looks like. So I don't know if I've shown you an example of this. I've put multiple different formats in this one space here. So the first one, K, is for black. O says I want dots. Dash says I also want a line. So there we go. That's Jenny's phone number, and then we have these points evaluated along the phone number there. And then if we want to represent an integration in a graph, we can use fill between. There's an underscore in here. Fill between, if we look at its arguments, it's going to want the x values, definitely wants a y value, and then y2 here is like the lower limit that it wants to fill. So this by default will fill down to the x-axis, which is what we want in this case. So fill between here, x and y. We can also use the standard commands like color, so let's make it red. And let's do something that's not solid. I don't know if we've used this one before, but let's use the alpha command, which is like a alpha represents how solid the color is. So we'll do 0.2 representing it's only 20% opaque, so 80% transparent. So if we run that command, we get this nice shading under there. And then I guess since we're already getting carried away being fancy, let's adjust our limits and let's try drawing some vertical lines underneath each of these points. So for the limits, our x-lim will go 0 to 7. Our y-lim is going to go 0 to, let's go 0 to 10, just so we have a little bit of space at the top. And then for drawing the vertical lines, we can do axv line, call that a number of times, but there's actually a command that will draw a list of lines, and that's called vlines. If we look at this, it's going to want x values, a y min, and a y max, and so it's going to draw, for the list of x values, it's going to draw a bunch of lines, each of which starts at y min, ends at y max. So in our case, our x values would be x, our y min are all going to be 0, and our y max are all going to be what we called y. We can also give this a color. I think by default it would go with blue, so let's make it K for black. And so there we go. We've made a picture that looks a lot like the trapezoid rule. Oh, you know what? I'm going to make that 6. Looks a lot like the trapezoid rule, so that we have all these trapezoids here. The shaded region is the area underneath, and that's exactly the area that is summed up by traps here in integrate. While we're at it, we could also use Simpsons Rule to integrate Jenny's phone number. Presumably this is a more accurate value of her phone number, at least in some sense. What Simpsons Rule is going to do is it's going to smooth in between these points with quadratic curves. So instead of having a bunch of trapezoids, it's got smoothed curve. So assuming that this data came from some kind of function that's supposed to generate smooth data, that would be the more accurate integration. So we do integrate.simps. If we pop up the documentation, it's just the same as for traps. So we're going to do y and x and see a more accurate estimate of Jenny's phone number's integral is 27. In general, if you're integrating an array, you would use simps over traps because in general your data is supposedly smooth. The places you wouldn't use simps are places where your data is very noisy, so it's like jumping up and down a lot rapidly, kind of suggesting that you don't have a high enough sampling for your data. In that case, the Simpsons rule is not any more accurate than trapezoid rule, so you would use trapezoid rule.